In this review video, we'll work through a set of real exam-style Calculus 1 problems on integration basics. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos, just the problem-solving portion without the lecture, so you can stay focused on the examples. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. We're going to walk through 5 very common general antiderivative examples, and I'll show you everything you have to think about when you're doing these types of problems. In these examples, we are going to find the most general antiderivative of the function. That means that we're going to have to include a plus c with our answer. The first example that we're going to look at is f of x is equal to 4 plus x squared minus 5x cubed. Just to make things easier, over here on the right, I've written down the function x to the n, as long as n is not equal to minus 1, and its antiderivative x to the n plus 1 divided by n plus 1 plus c. In this first example, I want to begin by rewriting our function little f of x as 4x to the 0 plus x squared minus 5x cubed. That x to the 0 is going to help us learn how to find the antiderivative. If you're finding the antiderivative of a little function f of x, then that antiderivative is typically notated as capital F of x. So we're going to say capital F of x is equal to 4 x to the 0, and then we're going to add 1 to our exponent and divide by that exponent. Now let's do the same thing to the next term. This is x to the 2 plus 1, all divided by 2 plus 1, and then we have minus 5x to the 3 plus 1, all divided by 3 plus 1, and then we have to add a plus c. This gives us capital F of x is equal to 4x plus 1/3 x cubed minus 5 over 4 x to the 4th plus c. And that's our final answer. In our second example, we're given the function little f of x is the 4th root of x cubed plus the 3rd root of x to the 5th. I chose this one because I want to show you that before you find the antiderivative, it's best to rewrite the function. So we're going to rewrite f of x as x to the 3/4 plus x to the 5/3. Now we can find the antiderivative much easier. Our antiderivative is capital F of x, and then it's going to be x to the 3/4, and we're going to add 1, and then we're going to divide by that exponent, 3/4 plus 1. And then we're going to do the same thing to our second term. This is x to the 5/3 plus 1, all divided by 5/3 plus 1 plus c. Let's go ahead and simplify this. 3 over 4 plus 1 is 7 over 4. So this is x to the 7 over 4, all divided by 7 over 4. And then our next term is 5 over 3 plus 1. So that is 8 over 3. And then we divide by 8 over 3, and we have our plus c. And then we're going to write our final answer in a little bit easier form. We're going to take the 1 over 7/4 and we're going to write it as 4 over 7 x to the 7 over 4 plus 3 over 8 x to the 8 over 3 plus c. And there's our answer. In our third example, we're given a function little f of x is equal to 5 minus 4x cubed plus 2x to the 6th, all divided by x to the 6th. Because we have one term in the denominator, we can break up our function into 3 separate pieces and then write each piece as x to a power. Doing this, we can write f of x as 5 over x to the 6th minus 4x cubed over x to the 6th plus 2x to the 6th over x to the 6th. You can only do this when you have one term in the denominator. We now need to rewrite this so that each term is x raised to a power. This is f of x is equal to 5x to the minus 6 minus 4x to the minus 3 plus 2. Now we can go ahead and take the antiderivative. Our antiderivative, capital F of x, is equal to 5x. Now we're going to add 1 to the exponent, and we get minus 6 plus 1, all divided by minus 6 plus 1, minus 4x to the minus 3 plus 1, and we divide that by minus 3 plus 1, and then we have a constant 2, and we're going to multiply that by x, and then we add on our constant c. Let's now simplify this. This is capital F of x is equal to 5x to the minus 5, all divided by minus 5, minus 4x to the minus 2, all divided by minus 2, plus 2x plus c. Now we just have to simplify it once more, and we'll get our answer. Capital F of x is equal to minus 1, all divided by x to the 5th, plus 2, all divided by x squared, plus 2x plus c. And there's our final answer. Our last 2 examples are different than our first 3 because they involve exponential and trigonometric functions. In example 4, we're given the function little f of x is equal to 5e to the x plus 2 divided by x. We don't have to simplify this function at all. We can just go straight ahead and take the antiderivative. Capital F of x is equal to 5. The antiderivative of e to the x is just e to the x. So we have 5e to the x plus 2 times 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x, and then we add on our plus c. And there's our answer. In our 5th example, we're given a function little f of x is equal to 2 sine x minus secant squared x. We also don't have to simplify this one before taking the antiderivative, and we can just go ahead and take it. Capital F of x is 2 times the antiderivative of sine x. The antiderivative of sine x is minus cosine x. And then we subtract off the antiderivative of secant squared, and that is tangent x. And then we add a plus c. We can rewrite this as capital F of x is minus 2 cosine x minus tangent x plus c. We're now going to walk through an example where we're going to evaluate a Riemann sum. We're going to evaluate the Riemann sum for a function f of x is equal to 2x minus 4 over the closed interval from 0 to 3 using 6 subintervals, and then taking the sample points to be right endpoints and then left endpoints. Just to make things easier, over here on the right, I've written down the formula that we need to use to evaluate these Riemann sums. I went ahead and graphed the function y is equal to f of x, which is equal to 2x minus 4. And I broke up our region into 6 subintervals. Notice that our values of x go from 0 to 3. We're going to start by calculating delta x. Our delta x is equal to b minus a all divided by n. So this is just 3 minus 0 divided by n, which is our number of intervals. And in this example, we have 6, so we're going to divide it by 6, and we get a value of 1/2. I'm going to highlight that because we're going to need that in a minute. Let's first find the Riemann sum when the sample points are right endpoints. Since we have 6 subintervals, we're going to write our Riemann sum as r sub 6, and it's equal to the sum, looking up here at the formula on the right, from I is equal to 1 to 6 of f of x sub I star times delta x. And our f of x is equal to 2x minus 4. Since we are using right endpoints to calculate the height of each rectangle, that's these points right here, we can say that x sub I star is just equal to x sub I, and the formula for that is a plus I delta x. A is our left-hand endpoint, which is 0, so we just have I times delta x, which we calculated to be 1/2. So this is I times 1/2. And now let's see what these points are. I starts at 1, so this is going to be 1/2. And then when it's 2, we get 1, and then we get 3/2. We get 4/2, which is 2, and then we get 5/2. And then our last one is when I is 6. 6 divided by 2 is 3. R sub 6 is then equal to f at our first point, so that's f at 1/2, plus f at our next point, which is 1, plus f at 3/2, plus f at 2, plus f at 5/2, plus f at 3, and then all of this is multiplied by delta x, which we already calculated to be 1/2. Now we're going to substitute in that our function f is equal to 2x minus 4. This gives us r sub 6 is equal to 2 times 1/2 minus 4, plus 2 times 1 minus 4, plus 2 times 3/2 minus 4, plus 2 times 2 minus 4. And then our next one is 2 times 5/2 minus 4, plus 2 times 3 minus 4. And then all of that is multiplied by 1/2. Now let's add all of this up. I am going to collect all of these minus 4s at the end, and we'll do our multiplication first. We have 2 times 1/2 is 1, and then we have 2 plus 3 plus 4 plus 5 plus 6. Now we're going to subtract off our 4s. There are 6 of them, so we're going to subtract 4 times 6. And then we have our 1/2. Let's see what we get. We can add these numbers first. That's going to give us 10. And then we'll add these numbers. So that's 11. So we have 10 plus 11. And then we'll subtract off 24, multiply this by 1/2. And this gives us 22 minus 24. So this is minus 2 times 1/2. And that gives us a value of minus 1. And that's what our Riemann sum is equal to when we use right endpoints. Let's now do the same type of calculation, but now we are going to use left endpoints. Our formula is going to be the same. We have r sub 6 is equal to the sum, I is equal to 1 to 6, f of x sub I star, delta x. And our f of x is again 2x minus 4. Now what's changing is our x sub I star. Because we are using left endpoints, let's go back up here and I'll highlight these so you can see what they are. We're using these 6 endpoints. Our x sub I star is notated as x sub I minus 1, and this is equal to a plus I minus 1 times delta x. Again, a is 0, so this just gives us I minus 1 times our delta x, which is 1/2. The delta x doesn't change when you use left-hand endpoints versus right-hand endpoints. Let's now write down what these endpoints are. We're going to start with I is equal to 1, so that gives us 0. And then we have 1/2, 1, 3/2, 2, and 5/2. We'll squish it in there. Now let's write down what R6 is. It is going to be f at 0 plus f at 1/2 plus f at 1 plus f at 3/2. And then we have f at 2. And then lastly, we have f at 5/2. And all of this is multiplied by 1/2. Now we're going to substitute in that f of x is 2x minus 4. And we get minus 4 plus 2 times 1/2 minus 4. And then we have 2 times 1 minus 4. And then 2 times 3/2 minus 4. And then we have 2 times 2 minus 4. And then we have 2 times 5/2 minus 4. And we multiply all of this by 1/2. Now let's go ahead and let's add this up. We'll save the minus 4s for the end. So this gives us 2 times 1/2 is 1. And then we have 2 plus 3 plus 4 plus 5. And then we subtract off 4 times 6 because there's 6 of them. And we multiply that by 1/2. Let's see what this gives us. 1 plus 2 plus 3 is 6. And then if we add 4, we're going to get 10. And let's go ahead and add 5. So that's just 15 minus 4 times 6, which is 24, times 1/2. And this is minus 9 times 1/2, which gives us an answer of minus 4.5. And that's what our Riemann sum is equal to when we use left endpoints. Notice that these two answers are very different. The reason for that is that we only used 6 subintervals. The exact answer is equal to minus 3. So you can see that the exact value is between our two answers. If we use more subintervals, then our answer is going to get a lot more accurate. We're now going to work through 2 examples where we are going to evaluate a definite integral using geometry. A definite integral can sometimes be solved by interpreting it as an area or areas under a curve. In both of these examples, we are going to evaluate the integral by interpreting it in terms of areas. In our first example, we have the integral from 0 to 10 of the absolute value of x minus 5 dx. The absolute value of x minus 5 is the function that we're going to be integrating, and we're going to start by graphing this function. To make things easier, I'm going to write down the definition for the absolute value of x. It is a piecewise function, and it's equal to x when x is greater than or equal to 0, and then it's equal to minus x when x is less than 0. We can then write down that the absolute value of x minus 5 using the same pattern is x minus 5 when x is greater than or equal to 5, and then minus the quantity x minus 5 when x is less than 5. We are integrating our function from 0 to 10. So let's find out what our function is equal to at 0 and at 10. When x is equal to 0, the absolute value of x minus 5 is equal to the absolute value of minus 5, which is 5. And then when x is equal to 10, the absolute value of x minus 5 is just equal to 5. Let's also find what this function is equal to in the middle, where our function changes. So we get x minus 5 absolute value is just equal to 0. Now let's go over here to our graph and let's plot these points. When x is equal to 0, our function is equal to 5. And then when x is equal to 10, it's equal to 5. And when x is equal to 5, it's equal to 0. So our graph looks like this, which is what we would expect when we graph an absolute value function. Let's put here that this is 5, and then this is 10. Now we can interpret our integral as the area under these two triangles, this triangle and that triangle. So our area is 1/2 the base times the height for each triangle. We have 2 of them. So our area is 1/2 our first base, which is 5, times our height, which is 5. And then our next triangle is the same, 1/2 5 times 5. You can also think about putting these two triangles together, and then you would just have a rectangle with base 5 and height 5. This gives us an answer of 25. What we did was much easier than having to substitute our piecewise function in and integrate it. Let's now look at our second example. In this example, we are integrating from minus 5 to 0, and our function is 1 plus the square root of 25 minus x squared. We're going to start by breaking up this integral into 2 pieces because both of the functions that we are integrating have different areas. This is equal to the integral from minus 5 to 0 of 1 times dx plus the integral from minus 5 to 0 of the square root of 25 minus x squared dx. Let's start by looking at the integral from minus 5 to 0 of 1 times dx. Our function is equal to 1, so up here on our graph, I am going to draw the line y is equal to 1. And we're going to go from minus 5 to 0. Our height is equal to 1, and our width is equal to 5. So we can say that our integral is equal to our area, and that's our base times our height. Our base is 5, and our height is 1, so we get an answer of 5. Let's highlight this because that's part of our answer. Let's now look at our second integral. This one is definitely harder. We have the square root of 25 minus x squared dx. Our f of x is the square root of 25 minus x squared. And I think this is easier if we think about this as y. We can then square both sides and we get 25 minus x squared is equal to y squared. So we have 25 is equal to x squared plus y squared. So this is a circle with radius equal to 5. Notice now that we are integrating from minus 5 to 0. So we actually have 1/4 of a circle. And that circle looks like this, where this point is minus 5, and this point up here is 5, and that's 0. So we can say that our integral is our area, and it's 1/4 our area, which is pi r squared. So this is 1/4 times pi times 5 squared. And this gives us an answer of 25/4 times pi. Now all we have to do is add both of these up to get our final answer. So let's write down that our answer is going to be our first area, 5, plus our second area, which is 25/4 times pi. And there's our answer. We're going to walk through an example where we are going to find the accumulated area under a function. We're going to let g of x equal the integral from a to x of f of t dt, where f is the function whose graph is shown. Down here we can see what f of t looks like. We are going to find the accumulated area by evaluating g of x for the values x is equal to 1, 3, and 6. This example illustrates how g of x represents the accumulated area under our function f of t from 0 to any point x. I'm going to go ahead and recopy what g of x is. Let's put it right over here. G of x is the integral from a to x of f of t dt. If we look up at our graph of f of t, we can see that t starts at 0, so that tells us that a is equal to 0, and we're going to find g of 1, g of 3, and g of 6. Let's start by finding g at 1. All we have to do is we have to replace x with 1. So this is the integral from 0 to 1 of f of t dt. If we look up at our graph, the integral from 0 to 1 of f of t dt is this area right here. It is a triangle, so we can write our answer as 1/2 the base times the height. Let's see what that is. This is 1/2, our base is 1, and our height is 1, so we get the value 1/2. So g of 1 is equal to 1/2. Now let's find g at 3. This is the integral from 0 to 3 of f of t dt. Because we already know what the integral from 0 to 1 is equal to, we're going to split this integral up into the integral from 0 to 1 of f of t dt plus the integral from 1 to 3 of f of t dt. That way we don't have to do double the work. This integral we already found to be equal to 1/2, and then this integral is this area right here up on our graph, and because it lies below the x-axis, it is going to be equal to minus 1/2 its base times its height. Let's see what that is. G of 3 is then 1/2 minus 1/2. Pull this graph back down. Our base is 2 and our height is 1. So this is minus 1/2 times 2 times 1. And this gives us 1/2 minus 1, which is equal to minus 1/2. Let's go back up here at our graph because I want to show you something. Notice that in our graph, as we go from x is 0 to x is 3, there is more area under the x-axis than there is above the x-axis, which is why our answer is negative. Now let's find g at 6. This is the integral from 0 to 6 of f of t dt. Because we know the integral now from 0 to 3, we're going to split this integral up, and we're going to integrate from 0 to 3, f of t dt. And then we're going to add on the integral from 3 to 6 of f of t dt. The integral from 0 to 3 is equal to minus 1/2. Now we need to find this integral. Let's go back up and look at our graph. That integral is the area under this triangle right here. And this triangle has a base of 3 and a height of 3. So this part is going to be 1/2 base times height, and this is 1/2 3 times 3. Let's see what this gives us. We have minus 1/2 from our first integral, and then we have 1/2 times 3, which is 9. So this is 9 minus 1 over 2, which is 8 over 2, and this gives us a value of 4. This tells us that the accumulated area from 0 to 6 is equal to 4. It makes sense that our answer is positive because if you look at the red triangles, you can see that there is more area above the x-axis than there is below the x-axis. We're now going to walk through some examples where we're going to use part 1 of the fundamental theorem of calculus to find the derivative of the given function. Just to make things easier, I have written down the essence of the fundamental theorem of calculus here in this green box. The fundamental theorem of calculus tells us that if g of x is the integral from a to x of f of t dt, then dg dx, or g prime of x, is equal to f of x. Let's now look at our first example. We want to find g prime of x, and the fundamental theorem of calculus tells us that the derivative of g of x with respect to the upper limit x is the integrand, which is the quantity 2 plus t to the 4th raised to the 5th power, evaluated at the upper limit x. So this is just 2 plus x to the 4th raised to the 5th. And we'll go ahead and highlight that. Now let's look at our second example. Notice in this example that the variable x is in the lower limit. To use the fundamental theorem of calculus, the variable needs to be in the upper limit. So we are going to start by changing the limits of integration and writing g of x as minus the integral from 4 to x t squared sine t dt. Remember that when you switch the limits of integration, all you do is multiply by a negative. Now we can go ahead and find the derivative of g of x by using the fundamental theorem of calculus. We have g prime of x is equal to the integrand t squared sine t evaluated at our upper limit x. So we have our negative, and now we're going to have x squared sine x. And there's our answer. Let's now look at example 3. This example is different than the first two because in the upper limit, we have 1 minus 3x. So it is not a single variable. We can only use the fundamental theorem of calculus part 1 to find a derivative if we have a single variable in the upper limit of integration. So what we're going to do is we're going to let u be equal to 1 minus 3x. So g of x is now g of u of x. The integral from 1 to u of t cubed, all divided by 1 plus t squared dt. If you're thinking, I think I've done something like this before, think about the chain rule. That's exactly what we're going to use to find the derivative. The chain rule tells us that dg dx, when g is a function of u, which is a function of x, is equal to dg du times du dx. Let's see what this gives us. Let's look at dg du first. That is just the derivative of this function right here with respect to u. And now u is our upper limit of integration. So dg du is just this integrand evaluated at u. So this gives us u cubed all divided by 1 plus u squared. Now we have to think about du dx. U is given right here. So du dx is just the derivative with respect to x of 1 minus 3x. This gives us u cubed all over 1 plus u squared times this derivative, which is equal to minus 3. Now, we're not quite done. We need to put our answer back in terms of x. So we're going to use this value of u and plug it into our answer. This gives us the quantity 1 minus 3x cubed, all divided by 1 plus 1 minus 3x quantity squared times minus 3. And let's rewrite this as minus 3 times 1 minus 3x quantity cubed, all divided by 1 plus 1 minus 3x quantity squared. And there's our final answer. I think this problem was the hardest one, so you may want to go back and see if you can work this one on your own. We're now going to walk through lots of integral examples, both definite and indefinite, using common integral formulas. I've included an example of each type that you might encounter. Let's start by going over 3 techniques that you can use for evaluating simple integrals. The first technique is that you can multiply algebraic functions. The second is that you can divide algebraic functions, but you can only do this when the denominator has one term. And then the third one is when you are working with trigonometric functions, and for those, sometimes you need to simplify them with a trigonometric formula. We're going to walk through 4 examples where we are going to evaluate the given indefinite integral, and we'll use these techniques that I just listed. In the first example, we're actually not going to use any of these techniques because I thought it would be good to just start off with a basic one that doesn't involve any extra simplification. For this one, we just have to remember what the formula is. When we integrate a constant, we have to multiply by x, so that's 4x. And then the next one is 2x. We're going to add 1 to the exponent, so 2 plus 1 is 3. And then you divide by that exponent. And then our next one is 5 times the integral of e to the x, and that's just e to the x. And then we can't forget to add on plus c. And there's our answer. In our second example, we are integrating x times the quantity 1 plus 2x to the fourth. This is an example where we have one function multiplied by another function. When we go to integrate this, we want to start by multiplying these 2 functions out. This gives us the integral of x plus 2x to the fifth. We're just multiplying the x through. Now we can go ahead and do the integration. The integral of x is x squared divided by 2, and then we have a 2 times the integral of x to the fifth, and that's x to the 6 over 6 plus c. Now we just have to simplify this. This is x squared over 2 plus x to the 6 over 3. plus c. Now let's look at our third example. For this one, we are integrating 3x minus 2 all divided by the square root of x. Notice that we have one term in the denominator, and that means that we can divide each term in the numerator by this term. I'm going to start by rewriting the square root of x as x to the 1/2. That'll just make things easier. Now we can go ahead and divide each term in the numerator by x to the 1/2. So this gives us 3x over x to the 1/2 minus 2 over x to the 1/2. And we're going to simplify this before we integrate it. 3x divided by x to the 1/2 is just 3x to the 1/2. And then we subtract 2, and I'm going to rewrite this last one as x to the minus 1/2. That way we can use our formula, x to the n. Now we can go ahead and integrate. This is 3x. We're going to add 1 to the exponent. 1/2 plus 1 is 3/2. And then we divide by 3/2. And then we have minus 2x minus 1/2 plus 1 is 1/2. And we divide by 1/2. And then we have our plus c. Now let's go ahead and let's simplify this. In our first term, our 3's are going to cancel. And we just have a 1/2 in the denominator, so we can bring that up and write it as 2x to the 3/2. And then we'll bring the other 1/2 up and multiply by 2. So 2 times 2 is 4. So we have minus 4x to the 1/2 plus c. And there's our answer. The last indefinite integral that we're going to do involves a sine function. We need to simplify this integral before we can actually integrate it. And to do that, we are going to have to use a trig formula that relates sine 2x to sine x. And that formula is sine 2x is equal to 2 sine x cosine x. That's a really good one to memorize because it comes up a lot. Now we can rewrite our integral as 2 sine x cosine x all divided by sine x times dx. We can then see that our sine x's are going to cancel, and this gives us the integral of 2 cosine x dx. And we can just go ahead and integrate that. We'll bring out the 2, and then the integral of cosine is sine. There's no negative there. And then we tack on our plus c. And that's the answer. Let's now look at some indefinite integral examples. We're going to now walk through 5 indefinite integral examples. Remember that an indefinite integral is equal to a number and not a function. Our first example is the integral from 0 to 2 of the quantity 2x plus 5 times the quantity 3x minus 1. Since our integral is one function times another function, we want to start by multiplying out those functions. So this is the integral from 0 to 2. We can use the FOIL method to multiply this out. Let's multiply the first terms, so that gives us 6x squared. And then we'll multiply the outer terms, which is minus 2x. And then the inner terms, which is 15x. And then the last terms, which gives us minus 5. Since we have two terms with an x, we want to combine those before we integrate. So we have 6x squared plus 13x minus 5. Now we can go ahead and integrate. Our first term is x cubed over 3. And then we have plus 13. And then we have an x squared over 2. And then minus 5x. And this is being evaluated from 0 to 2. This is equal to 6 divided by 3, which is 2. And then we're going to have 2 cubed. You substitute in the upper limit first, plus 13 times 2 squared divided by 2 minus 5 times 2. And then we subtract off the lower limit, but the lower limit is 0, so we can just subtract 0. Now let's see what this gives us. 2 cubed is 8, so 2 times 8 is 16. And then we have in our next term right here, 4 divided by 2, so that's just 2. So 13 times 2 is 26. And then we subtract 10. So this is just 16 plus 16, which gives us a value of 32. Now let's look at our second example. In this example, we are integrating x divided by 3 minus 3 divided by x. We wouldn't have to, but I'm going to go ahead and rewrite this just to make it a little bit easier. I'm going to write our first term as 1/3 x, and then our second term as minus 3 times 1 over x. That just makes it easier to see that we are integrating x and then 1 over x. This gives us 1/3 times the integral of x, which is x squared over 2, minus 3 times the integral of 1 over x, which is natural log absolute x. And we're going to evaluate this from 1 to 3. We're first going to substitute in the upper limit of integration, and we'll combine the 3 and the 2, so we have a 1/6, and then we have 3 squared, minus 3 times natural log of absolute 3, which is just 3, minus our two functions evaluated at x is equal to 1. So this is 1/6 times 1 squared minus 3 natural log 1. I always like to write it like this so that I can remember to multiply that negative through to both terms. Now let's see what we get. Our first term is 9 over 6, and then we have minus 3 natural log 3, and then our next term is minus 1 over 6, and then natural log of 1 is equal to 0, so we don't have to worry about that term. 9 over 6 minus 1 over 6 is 8 over 6, minus 3 natural log 3. And then let's divide 8 and 6 both by 2. So that gives us 4 over 3 minus 3 natural log 3. And that's our final answer. I've included this next one because I think this one can be difficult. We are integrating 1 plus cosine squared theta divided by cosine squared theta. Whenever I see something like this, I always think, oh, maybe I can use the formula sine squared theta plus cosine squared theta is equal to 1. But then I see that in the numerator, we have 1 plus cosine squared theta, not 1 minus cosine squared theta. So using that formula is not going to help. Then I look at it again and I say, oh, we just have one term in our denominator. So what we can do is we can rewrite what we're integrating and divide each term in the top by cosine squared. Let's see what this gives us. This is the integral from 0 to pi over 4 of 1 divided by cosine squared theta plus cosine squared theta, all divided by cosine squared theta d theta. Now let's simplify this. 1 divided by cosine squared theta is secant squared theta. And then cosine squared divided by cosine squared is 1. And now we can integrate each of these terms separately. The integral of secant squared is tangent theta. You can always think when you're doing this type of problem, what function do I take the derivative of to get secant squared? And that function is tangent. And then the integral of 1 is just theta. and we're evaluating between 0 and pi over 4. This gives us tangent pi over 4 plus pi over 4 minus tangent of 0 minus 0. Tangent of 0 is equal to 0 because it's sine over cosine, and sine of 0 is 0. Tangent of pi over 4 is equal to 1, and then we add pi over 4. So our final answer is 1 plus pi over 4. We're going to walk through how to evaluate indefinite integral examples using U substitution. To make things easier, I've listed 5 steps that we can follow, and we'll go through these steps one by one as we work through each example. Let's start with our first example. We are going to integrate 2x times the square root of 1 plus x squared. The first step is to choose u. We are going to choose u to be the function whose derivative occurs in the integrand. So we're going to let u be equal to 1 plus x squared. Our second step is to calculate du and then solve for dx. Du is equal to 2x dx, and we get that dx is equal to du all divided by 2x. The next step is to substitute this back into our integrand and rewrite the integral in terms of u. We have the integral of 2x times the square root of 1 plus x squared, which is now u, times dx, which is now du divided by 2x. Notice that the 2x's cancel, and that's because we made a good choice for u. And this is the integral of u to the 1/2 du. I'm writing it like that because it's going to make it easier to integrate. Step 4 is to just integrate this new integral. We have the integral of u to the 1/2 du, and that is equal to u to the 3/2. You just add 1 to your exponent, and then we divide by 3/2, and then we add our plus c. And let's rewrite this as 2/3 u to the 3/2 plus c. Our last step is to just rewrite our answer in terms of x. This gives us the answer 2/3 u, which is 1 plus x squared, to the 3/2 plus c. And there's our answer. Let's now look at our second example. This is a little bit more complicated than the first one. We are integrating x squared times the quantity x cubed plus 5 raised to the 6th power. We're going to start by choosing u. I'm going to let u be equal to x cubed plus 5 because the derivative is 3x squared, and we have an x squared in our integral. U is equal to x cubed plus 5. And then our second step is to calculate du and solve for dx. Du is 3x squared dx. And this means that dx is equal to du all divided by 3x squared. Now let's go ahead and let's substitute dx and u back up into our integral. We have the integral x squared. Now we're going to have u raised to the 6th power times dx, which is now du, all divided by 3x squared. We're going to cancel out our x squared terms, and we're left with 1/3. We can bring that out in front of the integral, u to the 6th du. Our fourth step is to just integrate this new integral. We have 1/3 the integral u to the 6th du is equal to 1/3. We're going to add 1 to the exponent. So we have u to the 7th divided by 7 plus c. And then we'll combine our constants. And we have 1 over 21 u to the 7th plus c. Our last step now is to rewrite this in terms of x. And our answer is 1 over 21. For u, we substitute back in x cubed plus 5, raise it to the 7th power, and then add c. And there's our answer. Let's look at our third example. This is an example where we're going to use what's called back substitution, and I'll show you exactly how that works. Notice with this integral that we don't have a function whose derivative is in our integral. That means what we're going to have to do is choose u to be the more complicated part of the integral, and that is going to be x cubed plus 1. So we're going to let u be x cubed plus 1. Our second step then is to calculate du and solve for dx. Du is 3x squared dx. And that gives us that dx is du all divided by 3x squared. Now let's substitute u and dx back up into our integral. We have the integral of the cube root of u, and then we have an x to the 5th. We'll do something with that in a minute. And then we have dx, which is du all divided by 3x squared. Now we're going to simplify this. We can bring a 1/3 out in front. And notice that our x squared is going to cancel with our x to the 5th, and we'll end up with an x cubed. We have the integral of the cube root of u, and we're going to write this as u to the 1/3, and then we have an x cubed and a du. Here's where back substitution comes in. Notice that our integral has a u cubed in it, but if we go back up to step 1, we can see that we can write u cubed in terms of u. We have u equal to x cubed plus 1, so x cubed is u minus 1. That's called back substitution. Let's see what this gives us. We have 1/3 times the integral u to the 1/3 times x cubed, which we just found was u minus 1, du. Now we can go on to step 4 and do the integration. We have 1/3 the integral u to the 1/3 times u minus 1. With this integral, we have two functions that are multiplied, u to the 1/3 and u minus 1. And the way that we can integrate this is by multiplying those two functions out. So let's go ahead and let's do that. This gives us 1/3 the integral u to the 1/3 times u is u to the 4/3, and then we subtract u to the 1/3 du. And we can go ahead and integrate this. This is 1/3. U to the 4/3 is u to the 4/3 plus 1, which is 7/3. And we divide by 7/3. And then we subtract u to the 1/3 plus 1 is 4/3. And we divide by 4/3. And then we have our plus c. Let's simplify this by bringing the fractions that are in the denominator up to the numerator. Our first term is 3 over 7, u to the 7/3, minus 3 over 4, u to the 4/3, plus c. And notice that our 3's are going to cancel. And this leaves us with 1/7 u to the 7/3 minus 1/4 u to the 4/3 plus c. Now for our last step, all we have to do is rewrite our answer in terms of x. Our answer is then 1/7. Instead of u, we have x cubed plus 1, and we raise that to the 7/3, and then we subtract 1/4, and we have x cubed plus 1 raised to the 4/3 plus c. And there's our answer. We're going to walk through how to evaluate two definite integral examples using u substitution. To make things easier, I've listed 5 simple steps that we can follow to make u substitution easier, and we'll walk through these steps one by one as we walk through both examples. In our first example, we are going to integrate the square root of 3x plus 4 from 0 to 7. Our first step is to choose what we're going to let u be equal to. Our first choice should always be to make u equal to the function whose derivative is in the integral. I'm going to let u be equal to 3x plus 4. And then in step 2, we're going to calculate du and solve for dx. Du is equal to 3 dx, and that gives us that dx is du all divided by 3. Our third step is to substitute dx back up into our integral and rewrite it in terms of u. I'm going to not include the 0 and the 7 just for this step. We have the integral of the square root of 3x plus 4 dx is the integral of the square root of u. Here's u. And now we're going to plug in dx. dx is du over 3. And let's go ahead and let's rewrite this as 1/3 the integral u to the 1/2 times du. Our fourth step is to find the limits of integration in terms of u. So let's write down again what u is. U is 3x plus 4. Our original limit of integration started with x is equal to 0. If we substitute that into our expression for u, we get that u is equal to 0 plus 4, which is 4. And then we do the same thing for our upper limit of integration, x is 7. This gives us u is equal to 3 times 7 plus 4, which is 21 plus 4, which gives us 25. In step 5, we are going to integrate our new integral. Now we're going to put back in limits, but now they're going to be in terms of u. U is going to go from 4 to 25, and our integral is 1/3 u to the 1/2 du. That 1/3 came back inside. Now we'll go ahead and pull it to the outside. This is 1/3 integrating u to the 1/2. We're going to add 1 to 1/2, so we get u to the 3/2, all divided by 3/2. And we're going to evaluate this from 4 to 25. Let's first simplify our constants. The 2 comes up on top, and we have 2 3's on the bottom, so this is 2 over 9 u to the 3/2 from 4 to 25. This gives us 2 over 9 times 25 to the 3/2 minus u evaluated at our lower limit, which is 4, so this is 4 to the 3/2. Let's see what this gives us. This is 2/9. 25 to the 1/2 is just the square root of 25, which is 5. So we have 5 cubed minus the square root of 4, which is 2, and that gives us 2 cubed. This is 2 over 9. 5 cubed is 125, and then 2 cubed is 8. So this is 2 over 9. 125 minus 8 is 117. 9 goes into 117. Do you know why? Let me tell you about this real quick. If you take 117 and you add up the digits, you get 1 plus 1 plus 7, which is 9. And that's divisible by 9, so you know that 9 goes into 117. I just think that's a fun trick. This gives us 2. 9 goes into 117 13 times, and we get an answer of 26. Remember, whenever you are computing a definite integral, you're always going to get a number. Let's now look at our second example. For this one, I wanted to do a trig example, and this one is definitely complicated. To choose u, we want to let u be the function whose derivative is in the integrand. Notice that we have a complicated expression involving sine x, and then we have a standalone cosine x. That standalone cosine x can be our derivative. So let's let u be equal to sine x, and let's just see what we get. For our second step, we're going to find du. Du is equal to cosine x dx, and we're going to solve for dx, and we get dx is equal to du divided by cosine x. Let's now substitute this back up into our integral. We're not going to worry about the limits right now. And we're going to write this as the integral of cosine x times sine of sine x, which is now u, times dx, which is now du, divided by cosine x. Because we chose u properly, our cosines cancel out, and we just have the integral of sine u du. So our choice of u was a really good one. For step 4, we have to find our new limits of integration in terms of u. So let's write down u is sine x, and we're going to let x be equal to 0 first. This gives us u is sine of 0, which is 0. And then we're going to let x be equal to pi over 2. This gives us u is sine pi over 2, which is 1. So when we're integrating in terms of u, we're going to integrate from 0 to 1. Our integral is the integral from 0 to 1 of sine u du. This is equal to minus cosine u, and this goes from 0 to 1. So we have minus cosine 1 minus a minus cosine 0. Cosine 1, we just have to leave as cosine 1. So we have minus cosine 1 plus cosine of 0, which is 1. And we get an answer of 1 minus cosine of 1. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.